Welcome to your Capstone lesson on statistics and probability in Python. Capstone, Comprehensive Statistical Analysis Case Study. In this hands-on lesson, we will explore practical probability and statistics techniques in Python through a full case study. You will learn how to load data, analyze patterns, and test hypotheses using real datasets. Let us get started on your journey to becoming comfortable with statistical thinking and Python. Running the cell now. Think about how real companies find patterns in the data they collect. You will be doing the same today. Let us begin by loading the Titanic dataset using the Seaborn library. We will load real data about Titanic passengers using a library named Seaborn. We turn off warnings so they do not distract us. We import pandas for working with tables and Seaborn for loading the data. Seaborn gives us access to this popular dataset about who survived or did not. Import numpy as np. We set the random seed to 42 for reproducibility. We load it into a data frame named df. We print out the shape to see how many rows and columns the table has. Now let us look at the first few rows to get a feel for the data. Running the cell now. This output shows that the Titanic dataset contains 891 rows and 15 columns, giving us a moderate-sized dataset to explore. The preview highlights key variables like survival status, passenger class, demographics, and fare, which are essential for statistical analysis and hypothesis testing. This initial data check confirms successful loading and sets the stage for investigating patterns related to survival. Try thinking about what story the very first rows of a data table might tell you. Now let us talk about variables and simple probability. Step 1. Understanding variables and probability. Probability means how likely something is to happen. The Titanic dataset lets us ask questions like, what is the chance a random passenger survived? Let us start by exploring simple probabilities. Running the cell now. Remember, probability is never more than 1, and never less than 0. Let us calculate the chance that a random passenger survived. We use the survived column. Taking the mean gives the fraction who survived. This number is the probability that a random person from the ship survived. We print the result rounded to 2 decimals to keep it simple. Running the cell now. This output shows the probability that a randomly chosen passenger survived the Titanic disaster, calculated as the average of the survived column. Notice the value 0.38 means about 38% of passengers survived, which aligns with the lesson's goal of understanding probability as the likelihood of an event occurring. This simple calculation helps connect the concept of averages to interpreting probabilities in real data. If you were on the Titanic, would you feel lucky based on these odds? Let us move to descriptive statistics now. Step 2. Descriptive statistics. Descriptive statistics show us the main features of data in a summary way. Let us look at age and fare. We will check the mean, median, and standard deviation. These summarize typical values and spread. Running the cell now. Describing data can give us intuition before deeper analysis. We will find the mean, median, and standard deviation for age and fare. The mean tells us the average value. Median gives the middle. Standard deviation is how much values spread out. First, we calculate these for age. Next, we do the same for the fare column. Running the cell now. Here, we see the average, mean, middle, median, and spread, standard deviation, for age and fare in the dataset. Notice that the mean age, 29.7, is close to the median, 28.0, indicating a fairly symmetric age distribution. For fare, the mean, 32.20, is much higher than the median, 14.45, showing that a few expensive tickets raise the average, which the large standard deviation, 49.69, also reflects. Which do you think is higher, typical or average fare? Sometimes outliers change the mean. Our data has missing values, especially in the age column. We check for missing age values using isNull and sum. We make a copy of the data to be safe. We fill missing ages with the median age using fillNA. Median is less affected by outliers. We add this as a new column called age_filled. Now we check that there are no more missing values in the filled version. Running the cell now. This output shows that the original age column had 177 missing values, which the code safely replaced using the median age to fill those gaps. Notice how this step ensures no nulls remain in age_filled, preparing the data for accurate descriptive statistics without bias from missing data. This confirms the intent to handle missing values before summarizing age with mean and median. Now our data is ready for further analysis. Let us discuss discrete distributions next. Step 3. Discrete probability distributions. Discrete means values you can count. Examples are number of siblings or survived versus not survived. The binomial distribution models the number of successes in a series of yes or no trials. Let us simulate flipping a coin like the survival question. Running the cell now. Imagine using coin flips to understand yes or no outcomes. This is what we call discrete. Let us use NumPy to simulate flipping a coin 10 times in a row, repeated 1,000 times. We use NumPy's binomial function. N means number of trials, P is the chance of heads, and size is how many experiments. We simulate a standard fair coin. Each trial is like a yes or no event. We collect results for each experiment, how many heads out of 10. Finally, we print the average number of heads across all experiments. Running the cell now. This output shows the average number of heads obtained from 1,000 simulations of flipping a coin 10 times each. Notice that the mean is close to 5, which matches the expected value for a binomial distribution with p equals 0.5 and n equals 10. This confirms the code successfully modeled the discrete probability process of counting successes in repeated trials. Can you guess the average number of heads when flipping a fair coin 10 times? The Poisson distribution is used to model counts like number of siblings. We add a comment explaining that we'll simulate the number of siblings aboard using a Poisson distribution. We import the Poisson function from the scipy.stats library. We extract the desibs per column from the data frame to get the number of siblings or spouses aboard. We calculate and print the mean number of siblings aboard. We compute the Poisson probability mass function for 0, 1, and 2 siblings using the mean as the rate parameter. We print the probabilities for having 0, 1, or 2 siblings aboard with formatting for readability. Running the cell now. This output shows the average number of siblings aboard is about 0.52, which is the parameter for the Poisson distribution modeling these counts. The probabilities reflect how likely it is to have 0, 1, or 2 siblings, demonstrating the discrete distribution shape and how it predicts counts of sibling passengers. This helps connect the idea of using discrete probability to describe count data in real-world contexts. Poisson models are great for events you count but do not expect to be regular. Now we learn about continuous data and models. Step 4. Continuous distributions. Not all data is counted, some is measured, like age or fair. Distributions such as the normal and exponential help us model this kind of data. Let us see if age follows a normal, bell curve, shape. Running the cell now. Think about heights or temperatures for examples of continuous values. Let us visualize if age in our dataset looks normal. Comment, we will plot a histogram of the ages and compare it to a normal distribution curve. Import the matplotlib.pyplot module for plotting. Import the norm function from scipy.stats to work with the normal distribution. Extract the filled age data from the data frame into a variable called ages. Create a histogram of the ages with 20 bins, normalizing it to form a density, and set transparency and color. Find the minimum and maximum age values to define the range of our x-axis. Generate 100 evenly spaced values from the minimum to maximum age to use for plotting the normal curve. Calculate the probability density function values for the normal distribution using the mean and standard deviation of the ages. Plot the normal distribution curve over the histogram as a black line with width 2. Set the title of the plot to age distribution with normal curve. Display the plot to the user. Running the cell now. This histogram shows the distribution of ages in the dataset, with a smooth bell curve overlay representing a normal distribution based on the sample mean and standard deviation. Notice how the bars roughly follow the shape of the normal curve, indicating that age can be reasonably modeled by a continuous normal distribution. This visual comparison helps us understand how well the normal distribution fits real-world measured data like age. Does the histogram look like a bell curve to you? Normal distribution is common in many real-life cases. Waiting times between random events, like arrivals, often follow the exponential distribution. This comment explains that the example models time between events using an exponential distribution. We import the expon function from scipy.stats to generate exponential random variables. We generate 1000 random samples from an exponential distribution with a scale parameter of 2. We create a histogram of the wait times with 30 bins, using cyan color and some transparency. We add a title to the plot to describe what it shows. We display the plot on the screen. Running the cell now. Here we generated 1000 simulated wait times using an exponential distribution, which models the time between random events. The histogram shows a right-skewed shape with many short waits and fewer long waits, highlighting how this distribution captures the typical pattern of wait times. This contrasts with a normal distribution and helps us understand different continuous data behaviors. Exponential distributions are common when we wait for random things to happen, such as trains or emails. Let us explore sampling and the famous central limit theorem. Step 5. Sampling and the central limit theorem, CLT. We often take samples because we cannot see all the data. The central limit theorem says averages of samples will look normal, even if the original data is not. Let us try this with sample means for fare. Running the cell now. Sampling turns one big puzzle into many small ones. We will draw samples of fare, find their means, and plot what we get. We drop missing fares, then randomly choose 30 fares at a time, repeated 500 times. For each sample, we calculate the mean fare. We create a histogram to visualize the distribution of these sample means. We add a title to describe the plot, highlighting the bell-shaped pattern due to the central limit theorem. We label the x-axis and then display the plot to the screen. Running the cell now. This histogram shows the distribution of 500 sample means of the fare column, each calculated from 30 randomly selected fares. Notice the shape approximates a normal distribution, demonstrating the central limit theorem in action. Sample means cluster around the true average fare even though individual fares may vary widely. This confirms that taking multiple samples helps us understand the overall population better than relying on single data points. Notice how the means form a normal curve, even if fares themselves do not. Let us move on to making estimates with confidence intervals. Step 6. Confidence intervals. A confidence interval estimates a range where the true value likely falls. We will compute a 95% confidence interval for the mean age. Running the cell now. Confidence intervals are like saying, I am pretty sure the true answer is inside this range. We will calculate a confidence interval using the t-distribution. We calculate the 95% confidence interval for the average age. We import the stats module from scipy to access statistical functions. We select the age_field column from the data frame as our data. We count the number of entries in the ages data. We calculate the average mean of the ages. We calculate the standard error of the mean using the sample standard deviation divided by the square root of n. We calculate the 95% confidence interval using the t-distribution with north 1 degrees of freedom. We print the lower and upper bounds of the confidence interval formatted to 2 decimal places. Running the cell now. This output shows the 95% confidence interval for the mean age, calculated from the filled ages in the dataset. Notice that the interval, 28.51, 30.22, gives a plausible range where the true mean age likely falls, reflecting the precision of our estimate based on sample size and variability. This aligns with the lesson goal of using confidence intervals to quantify uncertainty around a sample mean. Most sample means would land between these two numbers if we sampled over and over again. Now, let us test a real hypothesis together. Step 7. Hypothesis testing. Hypothesis tests help us decide if differences are real or just random. Let us check, did women have different survival rates than men on the Titanic? We will do a 2-sample t-test. Running the cell now. Hypothesis tests help us make decisions with data, not guesswork. Let us test if the difference in survival between men and women could be due to chance. This line states the question we want to test regarding survival rates between women and men. We select the survival data for females from the data frame. We select the survival data for males from the data frame. We perform an independent t-test comparing survival rates between females and males. We print the calculated t-statistic which measures the difference standardized by variability. We print the p-value which indicates the probability that the observed difference happened by chance. Running the cell now. The output shows a very high t-statistic and an extremely small p-value, indicating a significant difference in survival rates between women and men on the Titanic. This means the difference we observed is highly unlikely due to random chance, supporting the hypothesis that gender affected survival. This confirms the intent of the code, to statistically test if women and men had different survival outcomes. If the p-value is very small, we think the survival rates were different for men and women. Time to look at how two variables relate to each other. Step 8. Correlation and covariance. Correlation measures how two variables move together. Covariance is similar but not scaled. Let us see if age and fare are related. Running the cell now. Can you think of 2 things in your life that might increase or decrease together? Let us calculate the strength and direction of connection between age and fare. We are adding a comment to explain that the next lines compute correlation and covariance between age and fare. We calculate the correlation coefficient between the age_filled and fare columns in the data frame. We calculate the covariance between the age_filled and fare columns in the data frame. We print the correlation value rounded to 2 decimal places for easier reading. We print the covariance value rounded to 2 decimal places for easier reading. Running the cell now. The output shows a correlation of 0.1 and a covariance of 62.56 between age and fare, indicating a very weak positive relationship. This means that as age increases, fare tends to increase slightly, but the effect is minimal. The code helps us quantify how these 2 variables move together, with correlation providing a normalized measure and covariance showing the combined variability. Try thinking whether the sign is positive or negative and what that means. Now let us use a simple form of prediction, linear regression. Step 9. Simple regression. Regression helps us predict one variable from another. We will predict fare from age using a simple linear model. Let us see if older people paid more or less. Running the cell now. Prediction can be powerful for understanding how variables impact each other. We will build and draw a simple regression model. This comment explains that we will fit and plot a linear regression predicting fare from age. We import the linear regression class from Sclern to perform the regression. We create a mask selecting rows where both fare and age_filled are not null to avoid missing data. We assign the age_filled column of the masked rows to X as the predictor variable. We assign the fare column of the mast rows to y as the response variable. We create and fit a linear regression model using x and y. We create a scatter plot of age versus fare with some transparency. We plot the regression line predicted by the model in red over the scatter plot. We add labels to the x-axis, age, and y-axis, fare. We add a title to the plot describing what the regression represents. We display the constructed plot with scatter points and regression line. We print the slope, coefficient, and intercept of the fitted regression model, explaining the effect of age on fare. Running the cell now. This scatter plot shows the relationship between age and fare, with a red line representing the best fit linear regression predicting fare from age. Notice that the slope, (0.37, is positive but small, indicating a slight increase in fare as age increases, while the intercept, (21.37, suggests the baseline fare when age is 0. This output confirms the model is capturing a trend, demonstrating how simple regression quantifies and visualizes predictions between two variables. Look at the slope sign. Positive means fare goes up with age, negative means the opposite. Now let us try predicting categories using logistic regression. Step 10. Logistic regression, classification. Logistic regression predicts categories like survived or not. Let us use age and class to predict if a passenger survived. Running the cell now. Logistic regression is widely used for things like medical outcomes, or, as here, survival. We will use logistic regression to see how well we can predict survival based on age and class. This code predicts survival using logistic regression based on age and class. We import the logistic regression model from scikit-learn. We fill missing values in p-class using the most common class found. We prepare the feature matrix X using age and filled class values, dropping rows with any missing data. We select the target variable Y, survived, matching the indices of X to align data correctly. We create and train the logistic regression model with a maximum of 200 iterations. We calculate the model's accuracy score on the training data. We print the rounded prediction accuracy. Running the cell now. This output shows that the logistic regression model, using age and passenger class, correctly predicts survival about 70% of the time. Notice that data missing values in class were filled with the most common class to ensure the model could train without errors. This accuracy suggests that age and class do provide meaningful information for classifying survival in this dataset. If accuracy is over half, our simple model is learning something real. Let us use our model to predict a new passenger's survival chance. Please enter their age and ticket class. This line is a comment describing the purpose of the following code block. We get the passenger's age as a floating point number from the user's input. We get the passenger's ticket class as an integer from the user's input. We use the model CLF to predict the survival probability for the given age and class. We print the survival probability formatted to 2 decimal places. Running the cell now. This output shows the predicted probability that a passenger with the given age and ticket class survived, which in this example is 0.25 or 25%. Notice how the logistic regression model uses these input features to estimate survival likelihood as a value between 0 and 1, reflecting the model's classification intent. This step demonstrates how to apply the trained model to new data for making real-time predictions. Try entering different ages and classes. Who does the model say is most likely to survive? Subscribe for more free practical data science lessons on YouTube. Let us change gears and work with a classic time series example. Step 11. Time series analysis. Let us briefly see how to work with data over time using passengers from an airline dataset. We will plot monthly totals and notice any trends. Running the cell now. Time series show us patterns and changes across months or years. We will download a dataset with monthly airline passenger counts and plot it to see the trend. We add a comment explaining that we'll load and plot airline passengers over time. We give pandas the URL to download monthly totals. We use read_CSV to load it as a table. We change the date column into true date time format. We make a line plot of passenger count by month. We label the x-axis as month. We label the y-axis as passenger count. We set the plot's title to monthly airline passengers. Finally, we show the time series visualization. Running the cell now. The line plot shows the monthly airline passenger counts over time, revealing a clear upward trend with seasonal fluctuations. This shape confirms the code successfully converted the month column to date time and plotted continuous time series data, helping us visualize passenger growth and recurring patterns. This step demonstrates how to prepare and graph temporal data for trend analysis. Can you spot upward trends or patterns by season in this plot? Practice. Try loading your own time series data and plot it. Look for cycles or surprises. Let us introduce the idea of Bayesian thinking. Step 12. Bayesian approach. Bayesian methods update probabilities based on new evidence. Let us use a beta distribution to estimate the chance a random person survived. We update our belief as we see more data. Running the cell now. Bayesian ideas help in everything from spam filters to medicine. We use the beta distribution as our prior belief, then update it with real survival data. We are estimating survival probability using Bayesian beta distribution. Import the beta distribution from scipy.stats for Bayesian updating. Count the number of survivors from the survived column in the data frame. Calculate the number of non-survivors by subtracting survivors from total entries. Create a grid of values between 0 and 1 to evaluate the probability density. Set prior parameters alpha and beta to 1, representing a neutral prior belief. Calculate the posterior beta distribution with updated alpha and beta parameters. Plot the posterior probability density function over the grid X. Label the x-axis as survival probability for clarity. Label the y-axis as density to indicate this is a probability density. Add a title to explain what the plot represents. Display the plot to visualize the Bayesian posterior distribution. Running the cell now. The plot shows the Bayesian posterior distribution for the survival probability, shaped by the observed data with a beta distribution. Notice the peak around the most likely survival rate, reflecting how prior beliefs, uniform, update to a more informed estimate based on actual survival counts. This visualization helps us understand the uncertainty and confidence in our estimate after observing the data. The curve shape shows what probabilities are more or less likely based on observed data. Now it is your turn to run a simulation using all these skills. Step 13. Mini-project, simulation. Let us model an emergency scenario, a lifeboat that can only save a fixed number of people. How many would be left if picking at random? Let us simulate and see. Running the cell now. Mini-projects like this help you build intuition by running many trials fast. Let us simulate a lifeboat that saves only 200 people, repeated 1,000 times. This comment explains that we simulate saving 200 people from the Titanic at random, repeating this 1,000 times. We determine the total number of people on board from the data frame length. We set the boat capacity to 200 people. We specify the number of simulation trials to be 1,000. For each trial, we randomly select 200 people without replacement and calculate how many are left behind. We create a histogram to visualize the distribution of people left behind across all trials, using 15 bins and an orange color. We add a label to the x-axis to describe what the horizontal axis represents. We add a label to the y-axis to describe what the vertical axis represents. We set the title of the plot to describe the simulation topic. We display the histogram plot to the user. Running the cell now. This histogram shows the distribution of how many people are left behind when randomly selecting 200 survivors from the Titanic passengers over 1,000 trials. Notice the shape centers around a consistent count, reflecting variability due to random sampling. This helps us understand the expected range of outcomes in a rescue scenario limited by boat capacity. Can you think of ways to make this simulation more realistic or fair? For the final mini-project, we will look for a real link between ticket price and survival. Step 14, mini-project, analyze real data. Let us do something practical, investigate if higher ticket price meant a better chance of survival. You will group passengers by fare bands and check survival rates. Running the cell now. Start thinking like a detective. Ask questions and let the data give answers. Let us divide fares into 4 bands and check who survived in each group. We use Pandas Cucut to split fare into 4 equal bands. We label the bands so they are easier to read. We group the data by those bands and compute the mean survival rate for each. We print a label for our results. We print the actual survival rates for each fare group. Running the cell now. This output shows the average survival rate for passengers grouped by fare bands, split into 4 categories from low to high. Notice the clear upward trend. Passengers who paid higher fares had progressively better chances of survival. This confirms our intent to explore if ticket price influence survival outcomes through grouping and averaging. Are higher paying passengers more likely to survive? The numbers reveal the truth. Before you finish, remember some essential good habits. Step 15, best practices and troubleshooting. When you work with data, always check for missing values, outliers, and suspicious zeros. Keep your code tidy and document your thoughts as you work. Exploratory analysis saves you from mistakes later. Running the cell now. A little time spent checking your data now saves hours later. Here are some tips to keep learning beyond this lesson. Step 16, extra tips. Try new datasets from Seaborn, Sklearn, or online for more practice. Break big questions into small steps. Read code out loud to catch mistakes and understand logic better. Running the cell now. Keep exploring and do not be afraid of making mistakes, that is how you grow. Challenge yourself with these fun exercises. Step 17, challenge exercises. 1. Try comparing survival by age group. Who had better odds, kids, adults, or seniors? 2. Rerun your logistic regression on new features. What changes? 3. Plot a time series of daily temperatures from another dataset. Share your results with a friend or online community. Running the cell now. Which challenge will you try first? Every experiment helps you learn more. Let us look back at what you have accomplished in this lesson. Recap what you learned in this capstone. You loaded real data, discovered hidden trends, tested ideas, and built models. You can now turn raw numbers into knowledge. Keep practicing and asking questions. Data science rewards curiosity. Running the cell now. Next, share what you learned or download more datasets and try analyzing them. Thank you for participating in this capstone lesson. Thank you for joining this lesson. If you enjoyed it, like the video and subscribe for more beginner to expert data science guides. Which topic would you like to learn next? Leave a comment below. Running the cell now. Wishing you happy learning and exploration. See you in the next video.